So we have obtained an optimal solution with a revenue of 780. Okay, can we do better? Let's look at the constraints. So for machine A, we're using the machine for 39 hours, which is just below capacity. And for machine B, we're using the machine for 13 hours, which is way below 40 hours. So yes, if we wanted to increase this solution, increase the revenues, we have a lot of slack capacity, unused capacity at machine B, but we have almost no capacity for machine A. So we call this the binding constraint. This constraint is actually holding us back. Okay, this constraint has a lot of slack. This constraint has almost no slack. So this is the binding constraint. Depending on your numbers, machine B could be a binding constraint for you, or both machines. Machine A, machine B, or both machines could be a binding constraint. So let's try to relax this binding constraint. How are we going to do that? Let's suppose we buy a second machine A. Okay. So when we buy a second machine A, the capacity goes from 40 to 80. Okay. Let's try to optimize again, and this time the capacity of machine A has doubled. Everything else stays the same. The capacity of machine A has doubled. Click solve. Okay. Now we have more than almost, we have doubled. We're making 0 chairs, 26 tables. Your answers will be different because you'll be using different numbers. We have increased our revenues from 780 to 1560. Okay, let's look at the constraints. For machine B, we still have some slack, but again, machine A is our binding constraint. So if we bought a second machine A, we could have an additional $780. So we would be willing to pay up to $780 for buying a second machine A. Now let's go back to 40 hours per week for machine A. Let's suppose we decided to make dinner table sets. Instead of selling chairs individually and tables individually, we want to sell each table with 4 chairs. Okay, so let's add a constraint that says the number of chairs should be 4 times the number of tables. Let's add that constraint, and that constraint will be number of tables minus 4 times chairs equals 0. Okay, so let's do that. So chairs will be multiplied by minus 4. Tables will be multiplied by 1. Okay, and this should be equal. This should be equal to 0. Okay, so let's do this. Here, sum product, parentheses. These are the numbers, comma. These are the coefficients, close parenthesis, enter. Okay, so here we have an imbalance because the chairs are not 4 times the table. But just as an example, I'm going to say 24 chairs, okay, 6 tables. Okay, so okay, so I did this wrong. So this chair should be 1 and this should be -4. Okay, yes. So now I know that when I have 6 tables and 24 chairs, there's a 1:4 ratio, 4 chairs for each table. And I want to add this constraint and see how the solution changes when we add an additional constraint. So I go to data, solver, okay. I add a constraint. I'm going to say this should equal this. Okay, this should be exactly equal to 0. Okay, and I click on solve. All right. So now I have $260 in revenue. Okay, I'm producing 1 table and 4 chairs. Okay, so this constraint is satisfied. Okay, machine A has slack, machine B has slack. However, this constraint is holding us back. Okay,